So our next speaker is Professor Jyotirmoy Sengupta. So after retiring from Tata Institute in Bombay, TIFR Bombay, he was for a short time in our Vivekananda University, and now he is in IACS Kolkata. So he will be speaking on Benford's law for symmetric powers of holomorphic new forms.
Okay, so I'd like to begin by saying a thank you to the organizers for inviting me here. So, of course, already said about Kalyan and Srini, so I don't want to repeat that. So, I'll begin the thing. So, this is about Benford's law. So, as I've written, so Simon Newcomb was an American astronomer and he was looking at, so he was observing log tables and he found that the pages which had leading digit 1 more were more worn out. That means they were more referenced. But this is a bias why it couldn't be other 2, 3, 9. He was working with base 10, log to base 10. But then later on, much later, in 1938, Benford made the same observation for a variety of sequences. So this bias, now known as Benford's law, so I've given the definition, they are all very natural. So I is an infinite subset, G is some real valued sequence, so those elements of I said that the first digit of Gi is 1. So you define the arithmetic density in the usual way as limit x tending to infinity, the number of x which is in this set, I intersection divided by the total number. And we say that the sequence, this is the definition I have given, but the fact is later on I am going to introduce something called log density, which will show that if this density exists, it must equal this automatically. Okay, so I'll come to that, and why I have written S in 1 inverse, let me see, where's the chalk? Okay, good. So I was considering leading digit 1, except, so instead of that, if I take a leading digits S, digits S, a given sequence, then the general result is that this density, if it exists, will be log B 1 plus S inverse. So I am taking S only 1, S equal to 1. So I am getting this. So then the set is said to be Benford. So of course, a criterion for the sequence Gi to be Benford is that if you take the log of Gi to the base B, that should be equidistributed modulo 1. Of course, here if Gi is non-positive, I define the log as 0. So examples of Benford sequences, okay. One which follows the law is Gn equal to n factorial, that one. And the most natural sequence, the identity map Gn equal to n does not follow, have the density. So it's not Benford. So okay, so suppose a set fails to be Benford in the sense it doesn't have the first density, which is called arithmetic. Then we move to another definition, a new density. This is very familiar to more or less called log density. So what is that? The same thing. I am starting with the same function, leading digit 1. So instead of counting the number of i's, I take the sum of I inverse, I belonging to I intersection, and divide by the total. Less than or equal to x, I inverse. Of course, so you can see from this that if I take my set I to be n, all positive integers, natural numbers, then this delta tilde n does exist and is equal to this. But this thing did, so this is an example where the arithmetic density does not exist, but the log density exists. And if we say naturally that the sequence is log Benford, if the logarithm density exists. Now, as I said in the remark, if a set, this is easy to check, arithmetic density, then it also has, and the two are equal. So if I define a Benford sequence to be one which has a density, then automatically has a log density and the value is forced to be this. Okay. Now I come to my interest. I'm not really a number theorist. I work in automorphic forms. So and my thesis was on symplectic geometry and representation theory. So from there I moved a long way out. Okay, so the setting is the theorem of basic theorem due to Jesse Thorner and his collaborators. So as I said, so there the basic setup is, so now my I is P, the set of all primes. All rational primes, and the function g from P to R is Gp equal to AFP, where Fz is equal to sigma n equal to 1 to infinity AFn E of nz. Z belonging to the upper half plane is an element of Sk gamma naught n. It's a primitive form, i.e. a normalized new form. New form of weight k, even of course, k to even on gamma naught n, trivial character. Yeah, so everybody in automorphic forms writes this in this way. Yeah, so I omitted this thing, non-CM. This is important. Okay, this way, why? Because by Deligne, the Ramanujan conjecture, which is a theorem, RC, a theorem says that mod lambda Fn is less than or equal to Dn, where D is the usual divisor function. Is the usual divisor function. Okay, so let me now, I've given Thorner's theorem, let me show it. So as f is as I said, then this density does not have any integer base b greater than 3. Those which AFPs have leading digit 1, their density does not exist. So it's not Benford. So naturally, if it is not Benford, the other thing to try is the other density, namely the log density, and they show that the log density does exist, and of course, exists means its value has to be this. So it is this one. So it is logarithmically Benford. So let me deal with my result that says theorem 1 holds for sim squared and sim cube. Okay, so a couple of remarks. Expectation should hold for higher symmetric powers of f. And the second, this is a very difficult question. If I assume Ramanujan-Peterson, does theorem 1, just the theorem 1, that is not Benford, hold for mass cusp forms for SL2Z? But here there is a big problem because the theorem of Thorner crucially uses the Sato-Tate law. The entire proof is based on that. And Ramanujan would get it, you can write lambda fp as 2 cos theta, theta p, where theta p is a 0 pi. But how the cos theta p, whether they actually distributed according to that law or any measure absolutely continuous with respect to Lebesgue, that's we don't know for mass forms. So let me give a sketch of the proof of theorem 1 for sim cube. This in some sense is easier. I mean, intuitively it's easier. So let me explain why. So what is sim cube f? So by definition, more or less, and lambda, this is important, the normalized coefficient which is less than or equal to dn. Sim cube f at a prime p. This is the sequence I am studying now. As p varies over primes, this is nothing but lambda f of p cube. Okay, and this is generally true. Lambda sim mf of p is lambda f of p m. And we also have the Hecke relations, lambda f m times lambda f n is sigma d dividing the GCD of m comma n lambda f of mn by d squared. So using this you will get lambda sim cube f of p is lambda f p cubed minus 2 lambda f. Okay, so if I think in terms of the continuous variable lambda fp belonging to minus 2, 2, this is nothing but the polynomial x cube minus 2x. Okay, so let's draw the graph, high school. So at 0, this is 0, at 1, it is minus 1, and its maximum is at 2, that is 4. So I'll put it here, somewhere here, 4. So the graph is something like this. Okay. And it's an odd polynomial, this is this side. So why is this easy? Because you see, it will be just the mirror image. This is an odd polynomial, so this variable one, if it's a random, as you can see from here, the area under it basically cancels out. So it is mean 0, it is random that way, intuitively. Or in other words, what I am trying to say is, if you look at sigma p less than or equal to x lambda sim q f at p, this is small o of pi x, which in terms Sato-Tate is an asymptotic measure. So in terms of pi x, so the leading term is 0. That's what this says. And then you have to compute the values. Okay, let me just continue. So in his proof, in the proof, Thorna et al. Constructs some intervals where the primes won't satisfy some specific intervals. Okay, so let me just see if I've written that. No, anyways, basically to get the leading digit 1, so something like b power minus j and something by b power minus j plus 1 something, and so he wants to know he computes the Sato-Tate measure, and there is some, okay, so there is a lemma, but that gets more technical. So I'm saying ultimately you choose something where you want to show that this measure is has a lower bound. So here what you have to do is, you have to take the inverse image of this, because this is lambda f. Now you want lambda, so let me write, say, some suitable interval, say alpha beta. Belonging to, so this is odd, so let's put 0, 4. Note that mod lambda sim cube f p is less than or equal to number of divisors of p cube, that is equal to 4. So you can write, say, lambda sim cube f and p as 4 cos phi p, with just like the sim 1 f, that is f phi p belonging to 0 pi. And now this you put, and you have to take the inverse image of this and compute the integral. So that's not difficult to do, one has to be a bit careful, and it works. As I said, here it is intuitively clear because on the nose it is random, its mean is small o of pi of x. So the right amount of cancellation is taking place, and this measure becomes absolutely continuous. So you have to basically take the roots of this and find this thing. So that will again be some interval, and you compute the Sato-Tate measure of that interval, and that is positive. So that's how the proof goes for the first part. The second part requires a little more some more calculation. But I think it should be possible to do it by induction. Although I am not clear even to move from, so I should also give the square here. That's interesting for the proof. Lambda sim squared f p, this is now lambda f of p squared. So this is nothing but, by the Hecke relations, it is lambda f p the whole squared minus 1. So let's compute the mean of this. So I'm looking at sigma p less than or equal to x lambda f squared p minus, that is basically pi x, is just pi x, the second sigma 1. So if I want this to be random, I should better have this as 0, but this works out because if you compute this limit, then you will get that the leading term there is that you can put 2 cos theta p and compute. Actually, Ram has long ago he computed this for mass forms. In some paper, I think in Rocky Mountain Journal or something. So if the proof is the same once you write it in the same notation there. So that he had assumed Ramanujan, otherwise you can't proceed. So this is again random, so it apparently looks like this might be larger, but it's not. So the difference is small over pi x, and that's the crucial fact basically. And here is, as you see, it's easy to compute the measure. So if I want lambda f squared p, so where does this lie? -1, that is this. Now what's the difference here? This belongs to -1, 3, because this is non-negative. Minimum value is 0 and at a maximum 2 by 2 square is 4, 3. So this is asymmetric. So one might say that the average might become large, but then this shows that it is small over pi x. Maybe one can compute this breaking up. So if I write this as now 3 cos, let's write theta sim squared f of p, then cos theta sim squared f p belongs to -1, means it will give -1/3, is the value of the thing, and 1. So you take the inverse cos, this gives you 0, this gives you some pi by 2 from plus maybe 20 degree or something. And then you compute the measure. So if I have to compute this, say in a given interval, lambda, this is easier that way, f square minus p belongs to, say, an interval alpha beta belonging to my -1, 3. So what do I get then? Then I get mod lambda f p squared is 1 plus alpha comma beta. I mean this. But the minimum value of alpha is -1. So even if I put -1, 1 plus -1 is 0. So because the square has to be non-negative. Because lambda fp is all real. And at the maximum 3 it is 4, so it's root. So it's just the Sato-Tate measure twice, because mod lambda fp squared. So implies mod lambda fp is the Sato-Tate measure of the interval square root 1 plus alpha, square root 1 plus beta. Note that these are all positive. This is at least 0, so this is larger than 0, and because I mod lambda fp has to be this, so the total measure will be 2 times the Sato-Tate of this. And you can compute this. So then that would be 4 by pi. I think you write it in terms of cos inverse. So cos is a decreasing function. So the larger value will come here. Yeah. Beta, and there is a sign change when you take that measure. So if I change it, then I also get this actually. 1 plus alpha to, I have to check the sign, cos inverse square plus eta, then sine squared theta d theta. So you have to compute an integral like this. Let me see if I put the limits correctly. No, this should be below. This is smaller. Okay. So you can explicitly compute this and show it's positive, and you need it for certain intervals of the, say of the form like I have my fixed base B. So something like this intervals. And this you can prove. Yeah, so this is how the calculation proceeds for the square and the cube. Basically, once you handle these two, the higher powers are, if m is odd, then it's an odd polynomial. There are only odd powers there, and it's even, it's only even. So that way it should be possible to compute all higher powers, but I haven't checked everything. I checked only these two. Okay. So do I have, how much time I have? 5 more minutes? 4 minutes. Okay. So as I said, I don't know. This I posing a question because I think in one case this should be obvious. Namely, there's an example for mass forms. Old example of Sarnak, Peter. So Sarnak constructed some mass cusp forms on gamma naught D, where D greater than 0 is a fundamental discriminant. Discriminant having integer Fourier coefficients. Integer Fourier coefficients. I mean, this is normalized. Mass, it is always with lambda fn, Fourier coefficients. And he showed that they are attached to Galois, to two-dimensional even Galois representations with projective image, PGL2C image, either the dihedral group or the tetrahedral group. And by thy very construction, this mass form obeys the Ramanujan conjecture and Selberg at all places. This form obeys the Ramanujan conjecture at all places. All places, in particular, it has Laplacian eigenvalue for minus Laplacian, otherwise it will become a negative operator, is 1/4 at the bottom of the spectrum, and mod lambda Fp is less than or equal to 2. So here I think the Sato-Tet is nothing but Chebotarev density, right? So maybe one should be able to compute it for the symmetric part of this on the nose. Because symmetric square lift always exists. Gelbart-Jacquet proved it for anything. So, and cube also by Shahidi. So one would, this maybe as a toy case, one can try the Sarnak thing. It should work. And things should be very easy here. Okay, so that's what I wanted to say.